Thank you, Susan, for the invitation. Thanks to the committee as well. About 4 years ago, USGS received new appropriations to improve our fisheries assessment, including the evaluation and adoption of emerging technologies that could help us do our job better. At that time, we approached select members of the lake committees of several lakes with Fishery Commission facilitation, and we proposed 2 projects that were addressing key uncertainties that were hindering adoption or embracing of some of USGS's assessment results. The 2 projects that we proposed that the subgroup gave us consent to pursue, one of those was to address and quantify biases associated with our hydroacoustic assessment efforts through adoption of silent uncrewed surface vehicles. You'll be hearing about that work from Tom Evans in the talk to follow this one. And the second one was to try to develop a new approach to quantify round gobies that was agnostic to sediment to some extent and essentially was able to get into shallower waters and quantify them in rocky habitats, which the USGS bottom trawl program has historically been admittedly unable to do very effectively. So today I'll be talking to you about that effort, the second effort to quantify round gobies and create a new status and trends data set. Both of those projects were seen as 5-year efforts, and we're now entering the 5th year. So basically, this is a 4-year status update, and it's an update that I'm proud to report. We've made very good progress towards our overall objectives, which were to calculate a new lake-wide index of round goby abundance, to essentially use AI and image processing techniques to essentially accelerate the delivery of this index, which I'll describe in a minute. It's to essentially expand machine learning models to generalize these solutions that we're developing to the lakes that have clear water, which would be Lake Huron, Lake Michigan, and Lake Ontario. To compare densities with the bottom trawl effort, to also do a better job sort of discriminating between round gobies and sculpins, and eventually to support the results, the use of results in management. We've made excellent progress on the first 3 of these, with the exception of the sculpin discrimination, which I'm happy to report today will provide provisional results for 2020, 2021, and 2022 for lake-wide estimates of round goby abundance using this methodology. So the hardware we're using to collect data over the lake bed is essentially, it's an autonomous underwater vehicle. You could call it a torpedo of science that carries cameras. The cameras are located in the central hull section. We have a 12 megapixel color camera that's shooting monocular, and then we have a twin 5 megapixel color stereo camera. So essentially we're getting real-time estimates of 3-dimensional structure on the lake bed, which we're starting to tap into to quantify habitat structure. But we're using mostly the 12 megapixel camera for the round goby discrimination. This is a 200-meter rated vehicle that can essentially cover the entire depth distribution of round gobies, including their winter distribution, but we've been focused in the summer primarily. The way we deploy this is along 10-kilometer transects. We do between 25 and 30 of those per lake per year. We've now worked in Lake Michigan for 4 years consecutively since 2020. We fly at 1.7 meters off the lake bed. Each of the photos that we collect at either 5 frames a second in 2020, 2021, or 2 frames a second since then are geo-referenced, so we can basically place them on the lake bed on a map. Within those images, the big challenge is really to find the fish. And in the shallow 0 to 40 meter zone, that's mostly round gobies. And we've initially did that with human observers, and we've since moved that into an automated AI-driven process. Once those fish have been labeled, which is what we call that process, we then have the ability to fit different size estimators to them. Once we have their length, we can convert to weight using length-weight regressions. And once we have that, it's essentially a tabular effort to get to a lake-wide estimate. One thing I'll note is that to avoid double counting, we're essentially looking at every 25th photo on the bottom, which provides about a 2-meter separation between the leading edge of one photo and the tailing edge of another. So we're avoiding double counting. In reality, what we're doing is a more complicated process that started out with a lot of these blue boxes, which are manual steps in this process. Initially, we would look at an image, we would gauge whether it had good enough exposure and clarity to interpret it. We would then pass it to another set of users who would find all the fish in them, trace those individuals. And that was, as you can imagine, very arduous, time-intensive process. Which is essentially unreasonable to do year after year. The benefit, though, is by labeling many images, tens of thousands of them, we can use those images and train the computer to find the same patterns in the pixels and shape and size and textures that are contained in the images where round gobies were located. And so essentially since 21, we've been essentially able to successfully automate this entire process. And now we're sort of combining these little pieces of software into what you would call a pipeline to automate the delivery of the quantities associated with the survey. So we have an automated usability estimator, which is 90% plus accurate, which would throw out photos that are over or underexposed or too blurry because of turbidity. We have an automated goby detector, which we'd send the examples off for a subsample of QA/QC. We have a size and density estimator, and we have good algorithms for estimating substrate. I think most of us know that round gobies are more abundant in rocky substrate during the reproductive season, and so we believed from the beginning and have since confirmed that it's very important to consider substrate in our assessment. So using this approach, we essentially moved forward into our 2020 and forward assessment to get the new trend data set together. Essentially, the approach we're using is to use neural nets instead of trawl nets. And we're more or less relying on AI for goby detection. So what we've been able to do, and this is a major advancement in the last year, is we can essentially, we have a computer algorithm that can place a bounding box over an algorithm with reasonably high accuracy. That's a neural net that takes manually labeled images initially and couples them with the raw images they came from. It trains a deeply layered neural network to find the patterns where the gobies are present, and it'll put a bounding box in red here with a probability associated with it around each goby. So essentially, one advantage of this is that as our algorithms improve through time, we can catch and recatch these same fish. We now have images of the fish that have, of the bottom with fish in them, and as our methods get better through time, we'll be able to do this with greater efficiency. However, I believe at this time we actually have reasonable efficiency with our algorithm, especially if you compare it to the efficiency of conventional gears like bottom trawl or beam trawl. In this image, you can see this is a scene, a typical scene. The red boxes represent computer estimated locations of round gobies with associated probabilities. The black boxes are human labeled locations of round gobies that have been verified in triplicate. And so you can see that the computer estimate missed certain fish that the humans found. And in some cases, the computer will find fish that the humans missed. But in general, one of the other things that we've noted through a lot of data is that we can take the diagonal length from corner to corner of these computer-generated bounding boxes, and that it correlates nicely to the total length of the fish, which is what's reflected in this untransformed regression line here. So essentially, by placing the bounding boxes, by taking the diagonal length, we can get a reasonable estimate of fish lengths for all fish, for most fish that are present in these images. When I say most fish, essentially, this is essentially a process of iterative improvement of an algorithm. And the way we would judge the quality of the algorithm is through different skill statistics. So this is a probability threshold with a 1 being a 100% chance that a goby would be present and 0 the other direction. Two of the metrics that we're using are recall, which is essentially the percentage of fish that are truly present in the image that are captured by the algorithm. And then another one that would be important to this is precision, which is the proportion of bounding boxes predicted by the algorithm that actually have fish in them. So the algorithm has the ability to put a bounding box on an object that's not a fish. And as you get to a lower and lower threshold, it's putting more and more of those types of boxes out. So essentially what we can do is set our threshold at a level where we're offsetting the negative bias associated with missing fish with positive bias associated with essentially falsely predicting fish that are present. And that's essentially done at about a 0.3 or so probability threshold. So essentially what that gives us is an 82% efficiency of catching fish that are present, which again, a bottom trawl might get in the range of like 10 to 50% efficiency. 50% would be very high for a bottom trawl sample. And so we're already pretty high on the efficiency from that perspective. But there's also this sort of this false positive rate that is offsetting that. So essentially, this is a little bit different than a conventional trawl sample where you'd sample once and that's your sample. This is a little bit more complicated, but it's something that we can improve through time, but it's already performing well. Now we'll get to data. So far, we actually have 4 years of data, but I'm only presenting through 2022 today. You can see that in each of the years, we had more than 20,000 images that we were able to quantify, at least 15,000 fish quantified in each of those sampling years. And these are the combined swept area that was assessed by the photos, which we can scale in real units of length, width, and area. The other thing I'll point out is that I'm actually missing an important site near Waukegan, so this isn't just a blackout here in our sample. This is something that some of my team omitted in their delivery of data to me. But you can see we're trying to get lake-wide coverage. And in addition, unlike the bottom trawl, we are working in the outer Green Bay, and we're also working in Grand Traverse Bay. So that's one difference with our survey to the bottom trawl survey. With these types of data, seeing so many fish, we can get excellent descriptions of this population. The height of these the height of the bars in this length frequency histogram reflect the effort in each year in part, but they also reflect the abundance of fish captured. And you can see in 21 we caught way more fish. The mean length of fish is shown here in each year. And you can also see, as expected, that round gobies are most abundant from 5 meters to about 20 meters depth, tailing off pretty precipitously to 50 meters. Now, before I show you the lake-wide estimates, I want to share the results of a lab study that we did that was dealing with another aspect of efficiency, which is our ability to detect fish in different types of substrate. So we did a microcosm experiment in the USGS lab in Ann Arbor, where we put a known number of fish in microcosms in sandy substrates and rocky substrates, and we essentially took repeated observations of them and counted the fish over and over again to see what percentage of the fish in each microcosm we could positively recover using cameras. What we found is that in this simplified cobble environment like this, that we could detect about 59% of the fish on average, and that in the sandy substrate like this, we got about 96%. The gobies do burrow in the sand. So we actually incorporated these percentages into our annual assessment estimates, which I'll show you in a minute. The other thing that we had to do was come up with an estimate of the coarse versus fine substrate on the lake bed. And instead of using the available GIS data, which are extremely coarse and admittedly inaccurate at the scale at which we're doing this assessment, what we tried to do instead was to use the available 3-meter LiDAR digital elevation model and essentially calculated a bunch of roughness statistics on it based on neighborhoods of pixels. And the neighborhoods that had greater roughness correlate to rocky substrates. So we used a machine learning approach where we intersected 8,000 or so estimates of coarse fine. These labels are actually reversed in this diagram if you happen to know South Manitou Island. But regardless of that, this algorithm performs well at about 85% recovery of coarse fine in these pixels. And so we use that to inform our estimate of the proportion of the lake-wide nearshore environment, particularly the 0 to 20 meter zones that were in coarse versus fine substrate, which when we begin to get into our arithmetic exercise, which is essentially a spreadsheet exercise, The way we do the bottom trawl estimate for lake-wide abundance and this one is we take the depth bin by substrate specific densities that we detected, and we multiply them by the area in each of the fine versus coarse by depth bin crosses, and we can come up with an area weighted mean biomass at the lake-wide scale between the 0 meter and 115 meter depth zone. And the reason we picked 115 meter is that it matches the bottom trawl range, which is to 114 meters. When we do this for 2020, we come up with a kilograms per hectare estimate of 9 plus or minus 2, and that incorporates the correction factor from our lab experiment, where we upweighted the densities in coarse substrate. When you compare that to the bottom trawl estimates, which for round goby biomass density, which you can see here, they come in at about well, in 2020, we had a limited bottom trawl, so our estimate was 300 times higher in 2020, about 6.2 times higher in 2021, and about 2.3 times higher in 2022, which when I bounced this off my colleagues in the bottom trawl program, they thought sounded a little low, but within the realm of possibility. We can also project these results spatially. These are shown in 5 meter depth bins. And you can see, first of all, that the maximum density was quite high in some of these bins, 268 kilograms per hectare. But the pattern of abundance tends to be focused somewhere around the northern part of the lake, and the east side of Lake Michigan, west side of Lake Michigan in 2021 and 22 respectively. Now, this is not just a Lake Michigan survey, so we have similar numbers for Lake Huron and Lake Ontario. So this is actually we can make regional comparisons. Ontario is still in production, but that's basically in process. So to summarize, we set out 4 years ago with pretty much no results in hand, just an idea. We now have delivered an initial sort of preliminary estimate of a new trend for round goby abundance that accounts for coarse and fine substrates. We've developed the AI infrastructure necessary to deliver this in a rapid time frame. So with that, I believe that in addition to verifying our 2023 data, we're hoping that our 2024 results, which we'll be carrying out starting in next month really, or next couple months, we'll be able to deliver those on the same time frame as the report for the bottom trawl. Therefore, kind of delivering on the objectives to do this in a timely and efficient manner. With the caveats that I shared in terms of the ability to improve some of the algorithms. We still need to improve this in terms of understanding sculpin abundances, which would tend to intergrade with gobies around 40 to 50 meters. And then we're also interested in carrying out a trawl comparison, 1-to-1, same water, same day kind of comparison. And of course, we'd like to extend our catch efficiency work to the field to replicate that result or see what the result is under natural conditions. So with that, there's a lot of folks to thank. I would certainly like to point out some key contributors, Vic Santucci, John Detmers, the folks at my center, Chuck Medengen is co-author, and the Great Lakes Fisheries Research Authorization Act, and the Great Lake Restoration Initiative has also been really important to this. So thank you very much.